So let's start today's lecture. Again, a little bit repeating. So, well, in the general goal is to understand the Hodge cycles. Let me see. The general goal is to understand the Hodge cycle for hypersurfaces, and even before going to analyze the Hodge conjecture, and even for Hodge hypersurfaces, it is difficult to this study. So at some point, I became obsessed to try to analyze by deforming the Fermat variety. Then xn plus 1d, maybe tj x to the j, and remember that this in the homogeneous context, this x to the j is xf to the g0, xn plus 1 to the gn plus 1, and the degree must, the sum of gk must be d. So this was the full hypersurfaces. At some point, I put this condition gid. Maybe today I explained id becoming just indices such that gk between d minus 2 and 0 for k equal to 0, 1. In a minute, I will go to the ID in the affine context. Let's just for the moment homogeneous. And okay, so and the reason that why we take monomials, not monomials such that their exponents of xi is less than d minus 2, because let's say the all homogeneous polynomials of degree d, maybe there is a group action, this GL all n plus 2 times n plus 2 matrices with determinant non-zero acts here. This action is just trivial. This is the linear action. Linear action. So this is, let's say, so if how it is, if I have let's say I have to associate something here, that this is f a as a matrix acting on x. So now look at x as x0, x1, xn plus 1. So a acting linearly on x, and then you evaluate f again here. So at the end of the day, the hypersurface given by f equal to 0 is isomorphic to the hypersurface given by this action fx equal to 0. So they are the same hypersurfaces. And it turns out that maybe one observation, maybe let's make in this why this perturbation appear near Fermat. So near Fermat, let's for this parameter space, let's call it T. So T, the will be in T. So this T is the collection of all this Tj. Near Fermat, we have this T. So then all homogeneous polynomials quotiented by GLN plus 2C. This is surjective. And I will not go into detail of this one, but it is an easy statement. So the idea is that near, if whatever there is, and actually what means this near? This means in a Zariski open Zariski neighborhood of x0 f Fermat x baba xn plus 1 to the d, and that then what means whatever there is a, so the statement is this one. There is a in this homogeneous polynomials of degree d, there is a neighborhood of the Zariski neighborhood of Fermat such that any hypersurface in this Zariski neighborhood up to action of GLN plus 2, it can be written in this format with all the exponents is less than -2. So this is not a kind of, if you are interested in to the all hypersurfaces, just considering this family, which is still a huge family. It has a lot of parameters, but well, a few monomials less, it's good for computation. Okay, so this is the reason. So I made also this translation to to affine. So x0 going to x0, neglect, cut. So going to x0 to affine chart x0 equal to 1. So we'll cut x0, I0, and all these exponent I will cut from my notation. In particular, you can easily see that this ID, let's return back to this my I notation in the affine context, 0 and d minus 2 to the n plus 1. So ID will be translated, I will redefine ID in this case. So I will use the note G in I such that AG is between n plus 2 to of D and 1 plus n plus 2 D. And okay, so this is the reason why I took this parameter space for hypersurfaces. And actually, there is there is one topic that I always miss in all my courses: complex geometry and Hodge theory. Except for a few examples of D and any complex deformation of hypersurfaces of this form. And so this is basically where it is, this quotient. Where is the quotient? This quotient is basically the moduli space of the hypersurfaces, except for some counterexamples, which has, for example, do D n equal to 2, D equal to 4. There, this we discard this case, but other than this case, this is the moduli space of hypersurface. Okay, so let's go to let me, so maybe I remember again also the HP and PXT. So I argue that in a neighborhood of a basis of this I'm using the notation of the Hodge filtration, but at the end of the main, for me this is F divided by F. Let's see what this is FP divided by FP plus 1 of XT. So I never use Hodge decomposition in this course, even so the Hodge theory started with Hodge decomposition. But for me, this Hodge decomposition notation, it is the quotient of the Hodge filtration. Hn xt deram Hn deram xt. So a basis of this guy is given by, and of course I am taking a Zariski neighborhood. It is given by omega beta x beta. And I am now using just affine notation. Dx, remember that dx is dx1 dx plus n plus 1, and then this is fn minus plus 1, and let's say a beta is between n plus 1 n minus p. And okay, and what else? And then beta will be in my I set. And for this reason, I defined, let's say, this IPQ. So this will be the set of all beta in I, such that we have this one. So here, beta in IP n minus p. So this means that at the end we have the knowledge of the basis of this kind. And actually, I will have to put a residue here, because this is given in the complement of a hypersurface. But by abuse of notation, I will not put residues. Anyway, this is and at the end I will need just I n half plus 1, I n half minus 1, and I n half and half. And in particular, so I took Hodge cycle H n of the Fermat. Now this x0 is the Fermat. Let's just complex copy, and I took it in the affine part. So affine part, this means that then it induces element in the primitive part of the homology. So this 0 is primitive. This 0 means that the parameter equal to 0. And then I define this PIs, omega I delta 0, I in and half and half. These are the only periods of the Hodge cycles which might not be 0. And then what else I did? The metrics. Let's say Pi plus G, I in ID, G in I n half minus 1 and half. Let me see. No, this is the n minus. So I define this matrix. Its rows are indexed by ID. Its columns are indexed by this guy. And let me explain once again. I plus G. When you make I plus G, then I plus G is in the desired domain. But the point is that it can happen that some coordinate of I plus G is strictly bigger than t minus 2. If this is the case, then you put Pi plus G equal to 0. Anyway, automatically I have this one. Automatically I plus G. If one coordinate of I plus G is bigger than t minus 2, then I will put Pi plus G equal to 0. If it is less than, then I am already in this this set, and then I will use this period. Okay, this is the preparation for the last lecture, and then let me go to the main theorem that today we want to prove, that the Zariski tangent space of the Hajj locus is canally isomorphic to the kernel of this matrix. So the periods of Hajj cycles are also useful to compute the Zariski tangent space, and I remember that this is this analytic scheme. So we are computing the Zariski tangent space of analytic schemes and putting these examples from algebraic geometry, that the tangent space of a scheme is different from the tangent space of the underlying variety. Anyway, in the proof of the theorem, we will get familiar to this V delta 0. Okay, so let's go to the proof of this main theorem. Okay, so let's begin to let me draw this interval between 0 and n plus 1. So here beta between 1 and 0 and half. So let's say, okay, so what is Hajj locus? So let's Hajj locus. So Hajj locus is just omega. Let's redefine omega beta up to some constant. It will be the same omega beta as before, but let's x beta dx, and this f to the proper weight. And if let me show you here. So you see that here actually this n minus p is the integral part of beta. So let's use this plus 1. There was a plus 1 also. So anyway, let's put this notation beta in I. So what is the Hajj locus? Hajj locus is omega beta delta t equal to 0, for which beta in I and the last, what else, and a beta less than, this is the middle one, before the middle one, and since I am working in the affine variety, this I have to discard the beta integers. Okay, so the locus of t's such that all these integrals are 0. Okay, so first of all, maybe I ask a question. If you have a variety given by zeros of holomorphic functions or polynomials, what is its Zariski tangent space? In this case, we have this bunch of holomorphic function. Remember that these are holomorphic function around 0, and t is the parameter space at I2. Okay, so Hajj locus V delta 0. So tangent space of okay, so this is the calculus problem of 150 years ago. You have a bunch of holomorphic functions, they are equal to 0. You define the variety as their zeros, and its tangent space is
a kernel of derivative.
Exactly, but the kernel of derivative, what it is you just write the Taylor series of these guys and just take the linear part. So it is the linear part of equal to 0. So just take all the linear parts, and this is this will be the tangent space. So this means that at the end of the day, in order, so you see that here really I am using the concept of scheme. I am taking all these equations, even that they might be dependent or independent, it doesn't matter. And I have to calculate the linear part of all these integrals. These integrals are holomorphic function in T, and put it 0, and this will be the tangent space. And okay, so this so let's this is step. So now the point is that I have to find a way to compute the linear part of these guys, and this is actually easy. As Felipe told, that we have to take the derivative of this guy. So let's so let's return back to this the definition dx f a beta. Maybe in order to get matrix Pij, I will change the notation from beta to I. So let's put I, because okay. So in order to compute the linear part, what I have to do, I have to make the derivation with respect to Tj, and let's see. You remember, these are our Tg. So I call it f at t. So f at t, these Tj's are here, and at the end of the day, this is f at t. This is something which depends on t. Okay, so let's go. So a basic formula from calculus. Okay. So something else also is that here sigma. This is let me which one I choose. As I said, here I have to put the residue of the differential form, or if I take this sigma delta 0. Remember that we have this x0, we have a delta 0 here, and by Gaussian sequence in the Gaussian sequence we had the map which makes delta 0 a cycle in the complement. So the sigma delta 0 in the Leray-Thom-Gysin isomorphism. Anyway, this is what by it's very simple fact that really here there are just variable. The only dependence on t is here. So up to the rush some integers at the end. This is what sigma delta 0 I plus 2, and then xi dxi, and f and then here there will be number here which is this I plus 1. Maybe in order to see that there is no negative sign, if you see that there is no negative sign, I have taken my perturbation with negative sign here, and that's why when I make this derivation of the fraction, there will be negative sign. But at the end, this constant doesn't matter. What matters is that there will be xi and then xj, because let's say ft is plus tj xj. So I am making derivation with respect to tj. So xj as the coefficient will pop up upstairs. So anyway, the moral of the story is that derivating this integral is not so difficult, and this is the heart of the proof is basically this one.
Hossein, wouldn't the denominator be squared, like 2ai plus 2?
2, no.
Because you are taking the derivative, so
let's say AB.
Yeah, so it's
Yeah, but there will be this. Let's the basic formula of the calculus: a to the b to the n. So that is this. This is.
b to the 2n.
But if you take b to the n, but there will be cancellation because there will be b to the n minus 1 upstairs cancelling with whatever. Okay, write it whatever you want. Right? B to the n, and then a prime bn plus a bn prime, and then there will be bn minus 1 coming here, and that then here there will be bn plus 1.
Okay.
So this is
Right,
this is just a calculus in a more sophisticated way.
Right. Okay. I believe. Okay.
Okay.
I see.
Anyway, what I'm saying that the near to this monomial, there will be coming this monomial of the perturbation. By the way, I have to say that whatever I am saying in a more sophisticated language in Guazan's book, it is under the name infinitesimal variation of Hodge structures. But there you will not see any integral, and you will see a lot of cohomologies and so on. But what I'm saying, computing tangent space is a matter of just calculus, not really too much fancy mathematics. Okay, so anyway, so we have so the heart of the proof is just this formula. So let's proceed. So one observation. So first observation, if AI, so the definition of the Hodge cycle, but I less than n half, n minus 1. In any case, for me, AI never will be integer because I don't want to care about, I want to have differential forms in the compact variety. Then these guys, omega I, remember that I have changed notation from omega beta to omega I delta t, have no linear part. So first, this is the first observation. And the reason, the reason is this one. So at the end, I am making since I am trying to compute the linear part, I have to make derivation and put t equal to 0. This means that at the end of the day, sorry, maybe I have to put here, there is a t, and then putting t equal to 0. So for this part, so this is basically, let me explain in this picture. So this was the middle part that the integrals are might not 0. This is the between n half minus 1 and half, the one which 1b for the middle part. So the one middle, this part, all the integrals, they do not have a linear part. And the reason is this one. When we make this derivation, then we land on this one, and you see that here, so this is because a I plus g, if you compute it, is still less than n half. And you have to argue, we have to take care about that really they do not have a residue at infinity, this problem of a beta not integer. But at the end of the day, when we make derivation and put it equal to 0, we are still less than n half, but less than n half, I have put all integrals equal to 0. This is the definition of the Hajj Locus. This means that automatically this will be 0, and then it will turn out that for I n half less than n half minus 1, there is no linear part. So one has to a little bit have to say, well, something that one has to take care at the end, I plus j might not be in I. And actually, if it is not I, maybe one coordinate of I plus j is bigger than d minus 2. But in the other case also, we will reach this situation, and I will explain that this will not bother us. and this will be at the end equal to 0. So the point is that now the Hajj locus, its linear part, is just given by integrals of differential forms, which are here, and this is exactly the part h n half plus 1 n half minus 1. So let's go further. So maybe I write again the formula. So up to this some rational numbers that for today everything will be up to some rational numbers. Then let's say xi dx f. So where I am n half, I have to take n half minus 1. Let me see. I am going to take n, so ai bigger than n half minus, so yeah, exactly. So here for this step here, I will have n half itself. So the only non-trivial integrals are this one. So I between n half plus 1, and up to some this number that it will not bother me. This is xi plus j dx f n half plus 1, and this is exactly my pi plus g period. And remember that these guys might not be 0. Okay, so we are almost done. Maybe what I have to say, if again, let's I will not write also sigma. So if some coordinate of I plus g is bigger than strictly bigger than d minus 2, then this one maybe I will explain a little bit. I put dx f n half plus 1 delta 0 is equal to 0. Okay, this has to do with some computations in the earlier chapters of the book. Actually, this one we have already discussed, but maybe let me a little bit explain. So okay, so the point is that when one of the coordinates in I plus g is bigger than d minus 2, this is 0, and this is again they said again now I am a Fermat. Just let me tj, this is ft, and this became now I, and then t equal to 0, and then here so the f0, which is the Fermat. So remember that in one of our classes we start computing these integrals for Fermat, and this is really easy computation. The main point is that, for example, if let's say I0 plus G0 is bigger than d minus 2. What this means? This means that you can write this integral as f0 n half plus 1, and then x0 d minus 1. No, let's see x1, because there is no, well, x1. For example, this is just for example. For example, the coordinate 1 is I1 plus G1 is bigger than d minus 2. And then what is this? This is another monomial, dx. And what is this? This is Genova up to constant. This is the derivation of f0 with respect to x1, x tilde dx is the same as f0 and half plus 1. But you can gather this one, then it will, there's some monomial, d f wedge something f0 and half plus 1. At the end, you will get that the f wedge something, the f0 wedge something, and then f0 and half plus 1. And remember that in one of course, I told that if you have df0 wedge something, you can reduce the pole order. And maybe I write the formula. The formula was like this. I minus 1 df wedge omega for any hyperset f to the I is the in the Rham cohomology is d omega fi minus 1. And then you apply this one, and then you take care that you are still in the compact variety. But at the end of the day, you get integrals of differential forms of pole order strictly less than n half. But since your cycle is a Hodge cycle, such integrals are automatically 0. So this is a little bit computations to do here, but this little computation will show that at the end pi plus g, when I plus one of the coordinates of I plus g is bigger than d minus 2, it is 0. Okay, so this is already done. Then we have computed the derivations of tj, these integrals. And we see that it's in when we do derivation with respect to Tj, we get a pi plus g, and pi plus g is 0 when one of the coordinate of I plus g is bigger than 1. And then so we have so this means that so let's leave it so what we wanted to compute is let me see the linear part of this one. But when we gather the linear part of these integrals at the end, we get this statement. So this is the pi plus g times this v are exactly the linear part of the this integral that we were looking for. Anyway, it is too much notation, too much computation. Even myself, when I forget my own writing, I become confused with whatever I have written. Okay, so now we want to go do some applications of this computing the tangent space. Let me share my well, the application I will do it in the next lecture. But let's let me introduce some few elementary problem first. Let me share my where is this share present now? Okay. So now this is the idea of the book, the proof. But so the applications of whatever we did, I will do it the next lecture. I am planning to go back to Noether-Lefschetz locus. Remember that we proved the Noether's theorem, and then I will say a few applications in the study of Noether-Lefschetz locus. But before that one, let's go to this. I will explain something. One of the things that at the end I did in my book, you see that the linear part of the integrals are useful to computing the tangent space. Actually, I started to compute the full Taylor series of all these integrals. These are the integrals which appears in our study of the Hodge theory of hypersurfaces. And it is a kind of surprising that it is possible to write down a closed formula for the Taylor series of these guys, and there are a lot of strange notations. So basically, there appear some rational number. There is this S parameters that we will put it at the end, 1 or -1. But these are a kind of the integrals of the Fermat variety. So, and today, what we did is basically the linear part of these integrals. And you see that there are a lot of computations going on. I don't know if I will talk about these applications of writing the explicit Taylor series of these guys or not, but something let me explain a little bit before going. One can get a lot of elementary problems out of this process of making Hodge theory more elementary. So let's go. Periods of Hodge cycles. Maybe I will try to explain it in. So there is one chapter in my book which I have gathered few problems which are a priori elementary in the sense that you can understand it by just linear algebra knowledge. Okay, so let me explain a little bit about this one. Okay, so here in this section, I have used the projective notation. So this means that I0 is back to my notation, and so maybe this is actually this will be the same ID, but this by notation that we used will be n half, and this guy is n half plus 1, n half minus 1. So anyway, you define these three sets. They are just multi-indices, and you take a matrix. You take a vector who is indexed by this by this guy. And these are, well, in this context, they are just some complex numbers. Because well, the idea is that I want to introduce some problem that you can think it without any knowledge of Hodge theory. Okay, so you take this vector, and by definition, for any I which is not in this set, PA by definition is 0. So let's define the Pij matrix, the whose rows and columns are indexed by this one and this one, and then we define this matrix. So the problem is this one. The rank of this Pij matrix is always bigger than or equal to 0. Well, if the vector P is not 0. And in the next lecture, when I am going to give an applications of computing the tangent space of Hajj Locus, you will see the geometric interpretation of this number here. So this is one problem that if you want, you can, if you are interested in Olympiad problems in a more heavy combinatorial way, this is one problem here. So something that in the next lecture I will use this guy. This guy for. So I will go to n equal 2 case, and this guy, in the case of surfaces, is d. If you compute it, it is d minus. I forgot. There's a d minus 3. Ah, okay. So this guy for n equal to 2 is d minus 3, and I will say what d minus 2 has to do with the loci of surfaces containing a rational curve or a line. Okay, this is one problem. Let me go to another problem, which is let's go to this problem 221. So one question. So it is interesting to ask when this rank is reached by this number. So when we have an equality here, when we have equality here, and the next problem is it exactly gives the equality. So for I in odd numbers A0 on and the permutation sigma of 0, let's define this PI. This is it's a little bit ugly vector, but at the end it is possible to introduce a vector such that this P, that the rank is this one, and this problem is actually, I don't know, I will have time to say, this has to do with the periods of the point is that there are a lot of P and half inside the Fermat. There are a lot of projective spaces of dimension and half inside Fermat. Fermat is of dimension n, so this means that these are algebraic cycles, and actually these numbers has to do with this the periods of these guys. And but as it is, this is just a kind of elementary linear algebra problem. So let's go to another problem. This is also this one also I will reach it in the next lecture. What the interpretation of this guy in terms of Noether-Lefschetz. Okay, so for n equal to 2 and d bigger than or equal to 3, there are no complex numbers such that the rank of this guy between 2d minus 7 and d minus 3. So so the issue of the rank of this matrix has some gaps. It cannot admit any number between the bigger, let's say bigger than this d minus 3. So there is no PIG with this rank. So the next lecture I will talk about this relation with this Noether-Lefschetz loci. But if so, all this well, Noether-Lefschetz loci is just Hajj Locus in the case of n equal to 2. And well, if you want another problem, this is elementary problem. This is the problem. This problem is basically the previous one, putting d equal to 0 and n arbitrary. And maybe so. Let n be an even number. Ik be the set. Here, for example, Ik you can define it as the subsets of 0 and a plus 1 of cardinality k. This feature is because d equal to 3. And then we consider again these vector of numbers for n other, which is not in it by definition. This is 0. We define that now I plus j in this case becomes ai union with j. Let it be the matrix whose columns and rows indexed by this respectively, and in its ij entry we have I union with j. And this means that if I intersection is not empty, then it will not be in let's say in here. So this P I union with j will be 0, and then the problem is that this matrix has this rank. Okay, so let me see what I can tell more. Okay, so let's. Okay, so I think I will stop here. So the next lecture, I will return back to Noether-Lefschetz locus. I will explain that Noether-Lefschetz locus is just Hajj locus in the case of in the case of surfaces, and there are a few open problems in the case of Noether-Lefschetz locus, and I will introduce them, and I will give applications of this computing this period pi, this matrix pi plus g, and so on. And once again, let's maybe write this one. Okay. So all this is story for arbitrary projective variety is formulated under the name infinitesimal variation of Hodge structure. This is to Griffiths and his co-authors. They're Griffiths, Harris, Carlson, Green, and EVHS. And okay, the language which is used is mainly using cohomological language, but the way that I presented it is just saying that this is just the study of integrals, and well, really just knowing the Griffiths basis of the Rham cohomology of hypersurfaces, we can proceed it with just computer integral and so on.